Hi, everybody. And it's really great to see you all, and thank you for coming. I'm David Gersten, the Director of Arts, Letters, and Numbers, and I want to welcome you all. And I want to welcome Michael Benson and Jim Green. And thank you both for bringing this conversation to our Sonship exhibition in the 17th Venice Architecture Biennale. Tonight's conversation is titled An Architectonic Technological Sublimity. And in addition to being shared in the Venice Biennale, this is also being broadcast live via Clubhouse in a room called Small Steps and Giant Leaps. And thank you, Jim, for setting that up. And welcome to everyone in Clubhouse. So I'd like to briefly introduce Michael Benson and Jim Green, and then offer a few very brief thoughts. So I'm going to start with some of the facts. Michael Benson's work focuses on the intersection of art and science. A writer and artist, in the last decade, Benson has staged a series of large-scale shows of reprocessed planetary landscape photography in major museums internationally. His last book, Space Odyssey, Stanley Kubrick, Arthur C. Clarke, and the Making of a Masterpiece, was published by Simon & Schuster on the 50th anniversary of the release of 2001, A Space Odyssey, in April of 2018. Benson has contributed to The New Yorker, The New York Times, The Washington Post, and The Atlantic, among many other publications. He's currently using scanning electron microscopes to focus on natural design at sub-millimeter scales for a project titled Nanocosmos. Michael is a founding board member of Arts, Letters, and Numbers, and a longtime visiting artist. He has changed our worldview many times, so thank you for being here, Mike. Jim Green. Jim Green is NASA's chief scientist. In a more than 4-decade-long career at the agency, including director of NASA's planetary program, he has led more than a dozen successful missions, including the landing of the Curiosity rover on Mars, the New Horizons flyby of Pluto, and the Messenger spacecraft to Mercury. Wow. It's just wonderful to have both of you here with us. I'm so moved to have you come together for this conversation. You know, when we opened this Sonship exhibition, as I said then, one of our primary hopes for this overall project is to broaden the spectrum of experiences that are understood as education. And another one of our primary hopes is to expand the spatial imagination that is understood as architecture. And I say this because in the deepest sense, many of our current crises, and there are plenty of them, can be understood as crises of comprehension or crises of understanding. And our search for shared questions, questions that bring us together, may bring the new understandings we need to address our challenges. Our shared questions may, in fact, transform us and our challenges in ways that we cannot yet comprehend. And in many ways, tonight's event directly speaks to these hopes, to our search for the shared questions that bring us together within the space and time of our solar system. You know, I often say that if you ask a physicist about light, they may say something like, well, it's the very structure, fiber of their work and their questions. And if you ask a photographer about light, they too may say something like, it's the very structure and substance of their work. If you ask an astronomer about light, a filmmaker, an architect, if they're a good architect, all will say something about light being central to their questions and their work. So light becomes a shared question, bringing us together, bringing together many, many diverse disciplines and ways of knowing. And tonight, we have the extremely rare circumstance where between these two people, Jim Green and Michael Benson, we have practitioners of many of these disciplines, of physics, photography, astronomy, filmmaking, and more. And so it is a great honor to have you come together here. And I want to thank both of you for joining us in this subject. And lastly, I want to say that tonight's conversation is being recorded. And at the end of the conversation, we will have some time for questions from the audience. Now, given that we're broadcasting in our Venice Biennale Zoom and in Clubhouse, I'm going to ask that people please post their questions in the chat if you're in Zoom, and if you're in Clubhouse, if you could send them directly to me, David, you'll see me at the top, in a back channel. Send the questions there, and then I'm going to do my best to share them with Michael and Jim so that everybody can hear all the questions. So now I will hand it over to Michael and Jim to begin the program. Thank you.
Thank you so much, David. I really appreciate that incredibly generous introduction. I couldn't be more pleased to be talking with my friend Jim Green. I've had the pleasure of having many conversations with him fairly recently, and we started a while back. And now to do it in this kind of forum is just, for me, it's a blast. It will be a blast. This being the Venice Architecture Biennale, I mean, you know, anybody who goes there understands that the definition of architecture is rather wide. Architecture is not just bricks and mortar structures on Earth. Architecture is many things. But it occurred to me that, you know, one way to approach NASA's achievements over many decades now, effectively my entire lifetime. I was born in 1962. Not that long after NASA was founded, is to look at it as a kind of architecture. It's an architecture that links the terrestrial with the extraterrestrial. Because the solar system is a kinetic archipelago, it can't be a fixed structure. It incorporates fixed structures on Earth, brick and mortar structures like NASA headquarters in Washington, the deep dish antennae that link NASA and its scientists, associated scientists, with deep space missions. So it's that type of architecture, but then it connects to, it basically spans the solar system. You know, that's an extraordinary thing. And I think that we humans focus a lot on negative things and things that are problematic and things like pandemics that ground us for a year and a half, but we don't necessarily think about some of our achievements. And I'm going to stop talking in a minute, but I do want to, you know, kind of set this up and you know, for Jim to answer. So we have an architecture that spans the solar system. It is connected to the most extraordinary technologies we've ever produced, among the most extraordinary, these deep space missions, some of which are orbiting, some of which fly by, some of which land on the planets, some of which look at other galaxies, the Hubble Space Telescope and the upcoming James Webb. And I've called it a technological sublimity because it is awe-inspiring. The sublime is about awe. I am in awe of it. You know, and it seems to be getting more sublime all the time, thankfully. So I like to keep my eye on that rather than, you know, focusing on a lot of the negative things that has been in the media sphere over the last few years. Anyway, I'll just ask you, Jim, do you agree that architecture is one prism with which to, you know, a prism to look through when considering NASA's achievement?
Oh yeah, David, absolutely. I mean, when you think about approaching developing a spacecraft, a mission, an activity, you always create an architecture. And what's really been fascinating, based on, you know, the theme that you have laid out here, is that the architectures that we develop leverage a variety of aspects, things that already exist. Things that we then improve on and expand. And indeed, light is one of those key elements that connects it. And the light being radio waves as we probe out into the solar system, make measurements, and then send that data back. So let me touch on a couple of these architectures. And we'll start with probably one of the architectures that we've built, and it's called the International Space Station, and it's about the size of a football field. All right, and indeed, it took 10 years to make. Now, I recognize, churches and things that humans build here on Earth, take after an architect creates the plans, it may take hundreds of years to develop and build. And so we've been lucky to be able to create architectures and then over periods of time put them together. 10 years, 30 missions, and we still are improving the International Space Station. We still have brought up, most recently, another module, a Russian module. That name in Russian is Science. It is a science module, and we're really looking forward to doing many different types of experiments over the hundreds and thousands, actually, that we've done in the last 20 years since humans have occupied space in space station. Now, one of the ways that space station communicates is through a space network, and that space network is called TDRSS, okay? TDRSS really stands for Tracking and Data Relay Satellite System. And that started in 1983, so many, decades ago. These are geosynchronous satellites that then can communicate with anything in orbit that then sends to one satellite, which then can send to a TDRSS satellite and another one, and then brought down at key locations on the Earth. And indeed, we have many tracking stations. There are 13 TDRSS satellites in space. Now, the next structure that we have put in place goes well beyond the Earth. And indeed, it starts with the building of large radio antennas placed in key locations around the Earth, like Goldstone, which is in California. They have a 70-meter along with several 34-meter dishes that they array to then listen to our missions as we go out to the far parts of our planetary system. We also have another large dish at Canberra in Australia. And then, of course, we now have completed the initial, what I'd call the initial survey of all the planets and the major bodies of our solar system. And so that has been done through this network of big dishes, which is called the Deep Space Network, or DSN. And then finally, we've started the process of indeed building another communication infrastructure around the planet Mars.
Yeah, no, I wanted to get into that. And in fact, before we get into that, if I may,
sure,
I would just, as a point of personal privilege, recall being at JPL, Jet Propulsion Laboratory in Pasadena, California, when Cassini, the big, vast, school bus-sized interplanetary mission to Saturn was approaching Saturn, and I was actually at their relatively modest control center at JPL, specific to Cassini, and it was about 3 months before Cassini arrived, and there was a screen on the wall, and you saw at the top a Saturn, if I remember correctly, and then Cassini, and then the planet down below, and somebody mentioned to somebody else, oh yeah, well, we're over Australia now, and I was like, I processed that, and then I realized what that meant was that Australia was panning by as the Earth turned, and that Cassini, which was rather high over Australia, the altitude was rather high, but yeah, just to view it as over Australia was a new way of looking at altitude, which kind of underlines this point, this point we're trying to make about an architecture that is both kinetic and static. Actually, even those dishes, if I recall correctly, they turn.
They do.
So everything's moving. There's no static thing in the universe. But let's talk about Mars then. One of the things that I think 99.9% of the human race and even 99.9% of Americans have not really sufficiently appreciated is that NASA, in a fairly stealthy manner, I mean, there have been sensational landings on Mars, but I'm not talking about the sensational landings. NASA, in a sort of stealthy manner, has constructed a satellite network around Mars that not only takes images of the surface and conducts research, those spacecraft conduct research themselves, of course, but they serve as relay stations, so that when a lander or a rover that lands, another type of lander, comes and lands on the surface, it can communicate with Earth via those or Mars orbiting spacecraft. Now, I find that fascinating, and I think about the greats like Konstantin Tsiolkovsky, H.G. Wells, Konstantin Tsiolkovsky, the great Russian pioneer of rocketry, who apparently didn't believe that his ideas would come to fruition at any time soon, and others, Goddard, the American rocketry pioneer. I sometimes wonder what they would think if they knew that this had been constructed in this kind of stealthy JPL way, where human spaceflight is taking billions and billions because it's so expensive to keep astronauts alive. And meanwhile, JPL, which is running the robotic spacecraft, is using their fairly small percentage of the pie to build such an amazing structure. It's a structure orbiting Mars.
It is. So it started actually with a couple important ideas. One was the concept of we're going to be sending a series of missions. We want to get down to the surface, recognizing that Mars can be, in terms of distance away, either as much as 4 or 5 light minutes to as much as 22 light minutes away. So it can be a significant distance. And therefore, if we want to communicate with it, we have to have something on the surface with it that's a big dish that can always point back to the Earth, or some sort of relay. And so indeed, starting with the Mars Global Surveyor and also the Mars Odyssey missions, we recognize that even though those are orbiters, they should carry with them some really critical capability to communicate with upcoming ground assets, knowing we were going to get down to the ground. So the next architecture was what was the bandwidth, what was the frequency, how we were going to implement that. And we implement it in a UHF band, in the ultra high frequency band. So on board then a series of missions, as I said, Global Surveyor, then Odyssey, then the Mars Reconnaissance Orbiter, Maven. And then as our international partners began also to join us and be part of it, we would put those systems, we call those systems the Electras, we would put those Electras on their missions, and that would be Mars Express and Trace Gas Orbiter. And we would pay for those, and they would integrate it, and then any asset sitting on the ground, whether it was NASA's or one of our international partners, like the European Space Agency, they can use it. They can take advantage of that architecture. So once we created that idea and we shared it, then we know our international partners will be able to use it very effectively, and that cuts down on the cost of what you put down on the surface.
Right. Fantastic. Underpinning all this is a history of deep history of fascination with what the Greeks called planetas, moving stars, means stars that move. Speculation about what they are all about. Mars was red; it became associated with war, etc. It wasn't until Galileo and others started using the telescope that we started to realize, wait a second, these things they have their spheres, They're not stars, and then obviously with the advent of space flight and the possibility to send telescopes in effect to those places, they became worlds unto themselves. And that's, and then you have this staggering history of the last 50, 60 years. But let's talk a bit about the purpose of these endeavors. Now there's the pursuit of knowledge, pure knowledge, of course, and we could characterize that as science, for want of a better term. That's purely scientific, hardcore research. Planetary scientists want to know about the composition of the atmosphere of Jupiter, et cetera. But that's just part of it. There are other motivations there. And we're all aware, I'm sure everybody listening today, I mean, we're, people in a clubhouse house room that has the title "Small Steps, Giant Leaps." I think I probably butchered that, but in any case,
no, that's right.
Okay, are very aware of this. We're all aware of science fictional speculations concerning settling on other worlds. Elon Musk seems to be very serious about at least establishing some form of settlement on Mars in his lifetime. That means our lifetime, I suppose. And then, of course, it doesn't take much dipping into sci-fi literature to learn about concepts such as terraforming other worlds. You and I, Jim, were just joking before this thing started, or I was joking about how we may be terraforming other worlds as we which is making them suitable for human habitation as we make our world less suitable for human habitation. But I just want to tell you a brief story about going to see Arthur C. Clarke in Sri Lanka way back in the early noughts. And in preparation for my first meeting with him, I got this big fat book of his called Greetings, Carbon-Based Bipeds, which was his collected shorter essays. Because people don't necessarily know or remember that Arthur Clarke, apart from being one of the best science fiction writers of all time, was also a prolific essayist and advocate for going into space prior to Gagarin and everything. I read this entire book. I started before getting on the flight. I read it during the flight. I finally got to the last pages before going to meet him. And at the last pages, after, we're talking about writing that spanned from the early 30s until, late 90s or early noughts. At the very end, there was a kind of, after all this utopian, advocacy for colonies off the planet and so on, he finally got to a kind of belated realization that maybe it's just possible that we won't really end up, having large colonies on other worlds. We may end up with something like research stations in Antarctica. And I found that kind of moving, that at the end of his long career, it was sort of settling on him. It was dawning on him that it might not quite be the way he and Heinlein and Asimov had envisioned it. So what can you say, Jim, about our goals as you see it, both overt and, let's say, subliminal goals? Why are we doing this?
Well, let me pick up a couple threads there, because I think it's real important. I love history, is to think back a ways, going back to Copernicus. We recognize that when Copernicus finally put forward the concept that the planets are orbiting the sun and not the Earth, that was revolutionary. Why was it so revolutionary?
Because of his title.
No.
Yes. But we'll get to that in a minute.
All right. Okay. All right.
Because the term revolutionary, which we understand to mean a decisive break with the past, came from his title on the revolutions of the celestial spheres.
Meaning something slightly different from his perspective.
Meaning a radical break. The Copernican revolution became that term comes from his title. Prior to Copernicus, revolution simply meant something turning rather than, you see? Anyway, I rudely interrupted you, and luckily you're a generous guy, and you're gonna, I hope, forgive me. But please proceed with what.
Well, here's the thought that is inescapable. Once people realized if that is true, then we are not so unique. We are one of the planets that orbit. Therefore, there may be or must be life on those planets. That to me really started the germ of thinking, of the inspiration that comes with science fiction, about what kind of life would be there, and then how Percival Lowell and everyone making observations and then building that case. Well, there must be life there because we see canals and we see structures. We see new architectures that are going on there that then, must be made by intelligent life. Now, of course, we know much more about these things. We know that we are the planet of life. So far, we have not found life beyond Earth. But we're also recognizing that life could have come and gone on these planets, that we, in our small window of living, such a small window over these great lengths of time, 4.6 billion years that the solar system has existed and evolved. And during that time, the sun has gotten hotter and the atmospheres have changed for a variety of reasons, not the least of which is being added to by impacts carrying material from comets and asteroids. And now we have a birth of life here, but we know the past of Venus, we believe now, was a blue planet that perhaps as soon as maybe 800 million years ago, it had a significant amount of water on its surface where life could have been there, but has come and gone, okay? And now, of course, we're also at Mars, making major discoveries on Mars, recognizing how similar Mars is to the Earth and how when we look at it, we can see what perhaps aspects of early Earth looks like. And it's because of that, we then can imagine the next big step. And then that's actually having humans be able to live and work on these planetary surfaces.
Oh, that brings me to my question. Do you think large, let's not call them colonies, maybe that's a loaded term, large settlements, cities, tens of thousands of people, are possible or desirable on Mars, for example? Now, but let me just say, I have made the point, and I'm not the only one, that the Sahara Desert in the full heat of the sun in the summer, and Antarctica when it's 70 below Celsius in February, in its winter, at the low point, the darkest days of, it's dark all the time there in the winter in Antarctica. My point is Antarctica and the Sahara are both far more hospitable to life than Mars, even at their most extreme, they're at their extremes. So plus, my understanding is that because of cosmic rays and so forth, human beings would have to live burrowed into the under the surface of Mars. So do you think that it's possible or desirable to have large colonies, large settlements on Mars, for example? Let's leave Venus out of it, where it's hot enough to melt lead. I think we're not going to be settling there anytime soon.
Well, my answer to your question is it's absolutely necessary for the survival of the human species, period. Now, why do I think that? You have to think about 7.5 billion people living on this planet today. In 2050, we're going to be pushing 10 billion people. And what does it take for this Earth then to collapse in its ability to be able to support that population? And so consequently, just from that aspect, the concept of also moving out into the solar system makes sense. In addition to that, we are uncovering a variety of opportunities through the resources that we see that will enable us in many different ways to be able to live and work on a planetary surface. We're going to start with the moon, probably one of the most uninhabitable surfaces you can get. You know, it's worse than Mars. I mean, it has dust problems, no atmosphere, and
it's a short ride home, though.
But it's a short ride home.
Yeah.
So as we learn to live and work on this planetary surface, we're gonna have to do a lot of things differently. We'll have to be sustainable. That's what we want to do for long periods of time, live there for days and weeks, perhaps months. And therefore, we need to use the resources. We need to also learn how to use everything we bring, minimize waste, all right? Get involved in a variety of techniques and capabilities we need here on Earth in terms of conserving our resources and being able to reuse things by reshaping them in different ways and providing opportunities to then minimize that waste and minimize the amount of material we need to resupply. Right. And some of the key things that we're finding out, like the resources in the permanently shadowed regions in the North and South poles, tell us there's several 100 million tons of water alone. And that means, you know, we can get access to that water. Water is hydrogen and oxygen. You know, you can split it apart, you can breathe the oxygen. You know, once it's split apart, you can also use it for rocket fuel. So it gives you an opportunity to develop a capability to leave from Mars or make things on Mars and move them to other locations, all right? Because Mars has vast resources to do that. And of course, water is water. It might be frozen in these permanently shadowed regions, but H2O, you can drink, you know, whether it's on the moon or it's on Earth, it's still H2O, it's still water. And so indeed, going to Mars will be a challenge, and going to Mars will be like what we do in the Antarctic. We have groups that will go down during the summer and come home, but there are people that stay the winter, all right? We've learned how to do that. We've learned how to do a number of things in these extreme areas that we will have to do on Mars and on the moon. But I firmly believe it's absolutely essential for the human survival of the human race that we trek out into the solar system.
Okay, let's talk about the survival of the human race. I think one thing many listeners may want to know is why are we focusing our energies on planetary exploration when we have such emerging serious problems here on our planet? Now, this is kind of an updated version of what you heard they were saying in the 1960s with the Apollo program. You know, we've got ghettos on fire in inner city America. Why are we landing on the moon? Now, I personally don't necessarily buy this argument, because the money saved by not, first of all, planetary exploration is not that much money compared to manned crewed missions and so forth. And it's not as if that money would go towards building schools and solving some of these problems. But separate from building schools, it's increasingly clear that we have this serious problem on Earth with climate change. And previously, NASA has largely confined itself to providing critical and important data from Earth observing satellites about what's happening. But the other day we were chatting, Jim, and you brought up possible ways that NASA could contribute to a solution to climate change, a type of planetary protection that is not saving us from incoming asteroids, but another type of planetary protection. And I've always found this idea fascinating, and I would like for you to describe. We were talking about megastructures here also.
Yes, we're talking about megastructure.
We're talking about architecture. We're talking, architecture on Earth. Most of the 99%, there's that figure again, of architecture that we know is designed to counter one Earth gravity. I mean, all the architecture we know.
Mm-hmm.
So let's talk about what could be done, what NASA could do to try to rescue us from this spiking temperature, the spiking temperatures on Earth produced by all the carbon we pumped into the atmosphere.
Well, in reality, space is our future, and it's a vast opportunity for us to be able to understand the physics of what's going on, how the origin of enhanced greenhouse gases, understanding the evolution of the sun, understanding yes. that over time we're going to become more Venus-like. So that's
rapidly at this rate.
Well, okay,
yeah.
But that's still in our future. Even if we had, if you could eliminate greenhouse gas emissions today, the sun over time will continue to increase. And we know, based on the evolution of planets like Venus, that's going to take us into a direction. So we want to be able to manipulate, one idea is to be able to manipulate the amount of energy we receive from the sun, modulate that, be able to block out a piece of the light, build a mega structure to do that. And conceptually, one would go to the moon with resources that are there, develop that material, using that material on the moon, melt it, put together panels, be able to create structures, and then be able then to move that into positions that will then block light. But how do we get to that far future? How do we get to a future that then enables us to then have the Earth evolve in a way that maintains the complex life that we have, that we love and need and dearly hold as we go into the future? We do it in small steps. One of the major steps, of course, is space provides us an infinite amount of energy in a variety of ways. In fact, several countries have looked at how one can develop spacecraft capturing directly sunlight and then beaming that down to Earth. Countries that don't have large reservoirs of even fossil fuels, where their energy has to be either nuclear or they procure those fossil fuels, and then we're then caught in the concept of how they emit greenhouse gases and turning fossil fuels into energy. So clean energy is critical, and there are many different ways to get it. And starting with structures in space, capturing energy, sending it to the Earth is another futuristic idea that requires much less of a structure, a much smaller amount of effort, but would have perhaps an enormous benefit to Earth. And one can envision a number of those going on at really key and critical places around the Earth. So these concepts, once again, are important not only for the immediate future and may play in areas of green energy, but also in the areas of long-term survival of the human race. I mean, hundreds of millions of years.
I'm glad you mentioned hundreds of millions of years, because recently I was writing a piece actually about using the electron microscope. But it was about how space is everywhere. Space is not just what's up there and larger than us. Space is also what's smaller than us, among other things. But I was researching Buckminster Fuller, because I ended the story with the story that has been making the rounds for quite a while now about Buckminster Fuller, who had projected colonies, space colonies, et cetera, many other things. Well, I'll tell that story in a minute. I found, as I was Googling Bucky Fuller, I got to there's Arthur Clarke again, a piece by him, short piece by him about something Fuller had envisioned, which was a vast globe-girdling ring at the equator high enough so that it turned with the Earth. That means geostationary orbit, rotating with the Earth, which could serve as a structure from which cables could be lowered and space elevators, thus solving the problem of the dangers of chemical rocketry and the expense of chemical rocketry, could be lowered if we had strong enough materials and so on. And so that then got me, this majestic vision of the Earth as the hub of a wheel, and the wheel enabling easy access to the universe. That majestic vision then reminded me of other things. I mean, first of all, Konstantin Tsiolkovsky, again, the great Russian rocketry visionary, he actually conceived of a tower reaching to geostationary orbit. And he did that after seeing the Eiffel Tower, which was being constructed then, And he thought, well, if it's high enough, if it was high enough, it would orbit, the top of the tower would be geostationary. It wouldn't be split, it wouldn't be ripped up by the forces in between geostationary and Earth. And then there's Ring World by Larry Niven and Dyson spheres, this idea that a very, very, very advanced civilization could simply tap all of the energy of their star by making a sphere all the way around. So if you don't mind, riffing a bit about
Sure.
such structures that might conceivably be possible in the distant future.
Well, in a similar way, a ring that's at what we call sun synchronous. In other words, it's polar. And so as we move around the sun, it slides with us, and then it's always pointing towards the sun. That's a wonderful orbit. We have many spacecraft in that orbit. They actually then have a perfect view of the Earth each and every time. Areas have the same lighting and therefore make it easier to compare. But what you're really talking about is, what are the next set of structures? What's the next architecture that we should think about and then begin to build that would enable one new technology after another that helps explore space while preserving the Earth? And many of these ideas are fitting in. I mean, a ring, that's at sun synchronous around Mars, where instead of it around Earth, enables then potentially light shining from that ring down on the planet and heating it up, heating the polar cap, releasing the water that's trapped in the polar cap. There's 1/7 of the ancient ocean of Mars locked in that north polar cap. If we could melt that, then Mars would begin its own process of becoming more Earth-like, because it was Earth-like in its past. So when we talk about terraforming, we're actually talking about how the environment has changed from a past environment and how to take it back to that environment.
Right.
And so it's not so foreign to the planet. It's important because it's timely. It's in our time, and it's our ability then to use those kind of resources. But this whole idea of building mega structures is really caught on in the astrophysics community. Okay, because when they look at exoplanets now, they're thinking about what kind of telescopes do they need to look for mega structures. All right, because those civilizations that may be out there certainly are not at our level, exactly at our level. They could be very advanced, and they could be well into the concept of mega structures that will enable civilizations to live and survive in those individual solar systems. And then it tells us immediately that there's intelligent life there. So the concept of these being so science fiction-y is would change completely if in one observation by an astrophysicist
Yes.
around a solar system at another star, observing a mega structure, we then would know it's possible.
Yeah, that would just blow everybody's mind, and
Of course
we'd have
it would.
all of that cultural dislocation. It would be
It
unbelievable.
would be another Copernicus moment.
Oh my God, it would be a revolution, revolutionary moment. You know, another thing that would blow everybody's mind, and perhaps more achievable in let's say within our lifetimes, although let's hope that the other one is, you know, could happen in our lifetime, is that you're talking about discovery of a advanced civilization.
Yes, of course.
But what about life in our solar system? And, you know, I'm preaching to the converted with you regarding Europa, the moon, the Galilean satellite of Jupiter, the second moon out after Io, which is an ice-covered ocean. We've established that fairly definitively with Galileo and the Voyager missions, and which has probably had more water than all the oceans of Earth combined for millions and millions of years, therefore probably has all the conditions necessary for life there. And I've been advocating for a very long time that, you know, in part because I would like to see, you know, I would like to see more money go to NASA, Jim, you know, shoot me, you know. I would like to see more focus on planetary exploration. And one sure way, absolutely sure way to achieve that would be to discover life under the ice on Europa. And happily, there's not one, but two missions, speaking of architecture in our kinetic archipelago of worlds, that are not just on the drawing board, but I think if I understand right, they're actually being constructed now. You know, and they will both be going to Jupiter. One is European and one is NASA, to investigate the icy satellites of Jupiter, more than one of which probably almost certainly have subsurface oceans that may have conditions suitable for life. So if you would be so kind as to talk about that for a minute.
Well, I was really privileged as head of planetary from 2006 to 2018.
Head of planetary science at NASA, meaning NASA. You were overseeing the entire planetary program.
Yes. And when I walked in 2006, you know, it was a very difficult job. We had all kinds of things going on. And indeed, the community, the scientific community at that time was really clamoring for a Europa mission. And I thought, that's exactly what I want to do. I want to get a Europa mission. Well, 10 years later, I got one. It took me a long time. And part of that was we recognized we needed more information. We were struggling with the architecture, knowing that a spacecraft getting into orbit around Europa in the radiation belt that it's in, that part of where the moon sits, makes that satellite last only a matter of a couple months.
Yes.
And that the data that we want to take is so voluminous, we'd have to have a lot of onboard processing, decision-making, just to send back the tidbits we want. And I didn't want that. I wanted a longer-lived mission that we then could take that high-volume data, understand it, and then have the opportunity for the scientific community to fine-tune the next set of measurements.
Right.
And then the discovery of the plumes. You know,
from Europa.
From Europa, yeah, that the cracks come and go and open and close. And we see what we believe, even from Hubble telescope, you know, we've been seeing these walls of water that go from the surface 400 kilometers up into space. Now,
yeah, you don't need to melt a submarine through the ice if you have a plume shooting into space, correct?
Correct. I mean, the last time I looked here on Earth, Old Faithful doesn't make it anywhere near that high.
Yeah,
and
right.
So it's a phenomenal thing. And the ability then to step back from afar, scour the planet looking for these plumes, and then target it and go back in and fly through a plume.
Yes.
We finally figured out that architecture, and that architecture was similar to what Cassini was doing at Saturn by leveraging constant flybys of Titan. And so by the time we then architect the new orbit, we then realized this is the way to go. And that mission's called Clipper. I had the pleasure of presenting that to the administrator, selling that to the administration, getting funding from Congress, and the stars aligned. And we got the money and we're cutting metal. So it's planned to be launched 23-24 timeframe. And in addition to that, working with the European Space Agency, I was also quite lucky, even though we all had ups and downs in our budgets and how we were going to work together, to have NASA be part of their mission called JUICE, which is the Jupiter Icy Moon orbiter, and it's going to end up orbiting Ganymede, which is indeed another spectacular moon of Jupiter. It generates its own magnetic field, and it's bigger than the planet Mercury. Right. Yeah. So it's just a beautiful, beautiful moon. But those steps will enable us, I think, to really get an idea of potentially the life that may be there, and could make some really startling discoveries.
Yes, indeed. And that would really take us to the next chapter. Now, I had some other questions for you, but I realized that it's 8:55 and it wouldn't be fair to keep on yammering myself. I'm speaking about myself, not you. You don't yammer, I yammer. And we should really open it, I think. If David would be so kind as to come back and moderate. I mean, I think there are probably a bunch of people in Clubhouse and a bunch of people in Zoom probably have questions for us. So let's go there.
Hi.
Hey.
Welcome back.
Wow. Thank you so much. That was absolutely beautiful. And I want to encourage people to send questions right now. I'm watching both the chat and the back channel in Clubhouse. So please do that. And while I do that, I just wanted to say, I mean, I have this incredible sense from listening to both of you of, in a way, I think something incredibly hopeful, which is our solar system as a continuous geography. Now, I mean, of discrete bodies, and we know there's a lot of distance between them. But if what I felt was that we can recognize this tiny little solar system of ours as a continuous geography of discrete bodies, and
exactly.
That brought me to then thinking about the interconnectedness of all of these discrete bodies, right? These planets, and then I somehow looped back to the point about the continents, and I was thinking, wow, the interconnectedness of our continents is a rather, let's say in terms of achievability, that should be obvious that it's, that it is a continuous geography, and that then that brought me to playing with this existential condition, right? Survival, life on Earth, survival in our solar system, and I was thinking about, well, I guess back to Copernicus, back to revolution, back to, and I was playing with state changes. So that's what I want to say is, water, vapor, ice, but we also know the political meaning of state changes, right? And I guess what I'm working on here, I'm fumbling with a kind of phenomenological relationship to the planet's social political challenges that could be advanced, understood, reimagined through this idea of a continuous geography of discrete bodies, right? Through this idea that there is a transformation possible in terms of how we perceive life on Earth, how we perceive each other, because we sure know we need a large evolution in our social political thing.
Yeah.
So true. So true.
Well, I would say this is another wonderful element of space. When you look at the number of astronauts from so many different countries that have been on space station, and even during times when there's been political unrest. I mean, we had cosmonauts on space station. When they left, it was the USSR. And when they came back, it was Russia, all right? And then we've had conflicts over time. But on space station, it's completely different. It's a shared experience for which the diversity makes it happen. It makes it work. It's different points of view, different solutions to problems, and in terms of their approaches that then enable us as humans to live and work in space and embrace these different cultures. So I think space provides us a common shared experience. It's a little bit like The Martian, okay? Where it was a human versus nature. How's he going to survive on Mars? And he was doing everything he could. Even if it was a team, they'd be doing that. The arguments between them would be unimportant. The concept of survival is it. And space is that frontier, I think, that's also providing that unifying theme that we should embrace.
And I think the great visionaries like Tsiolkovsky and others had this idea that, and Arthur Clarke, that Arthur Clarke wrote this beautiful thing about how going into space is equivalent to, in its audacity and its importance, to when life came out of the sea and went onto the land. And he had this beautiful line about how, that perhaps our civilization, our way of being on land, our whole period of history is suspended between the sea of salt and the sea of stars. And then he ended that with, now we must venture forth, in that grand way of his Clarke at his peak, in this kind of prophetic way. By the way, once I had fun, I was talking to him about how, I said, if Tsiolkovsky and von Braun, Tsiolkovsky and Oberth and von Braun, and Goddard are the Marx, Lenin, and Engels of spaceflight, then you're the Trotsky, the great propagandist of the revolution, And he kind of laughed and said there might be some truth to that, but then he pointed out that he didn't point out that he'd invented the communication satellite. So
the
I was
concept,
like, okay,
yeah.
Well, the concept,
of the geosynchronous ring, yeah.
Yeah, I mean, that's a complicated story there. To what extent he invented it. He was certainly a key proponent of geostationary orbit. Right. Yeah. But anyway.
Yeah, and yeah. I do have a question, but just before that, I think in what you were both saying, there is this thing about time. I mean,
yes.
In deep time, we know the space-time question has been wrestled with for quite a while, but I think there's another duration that could help us evolve beyond the incredibly short-sighted, myopic temporality that is, afflicting our economic and social political models. There's a lot to be learned.
Yes.
From deep space.
Well, we are the first species that recognizes that we can become extinct. We're also the first species that can do something about that. And space is that step that we need to take, then that gives us the views that allows us to look down and better manage resources. Our Earth science satellites can understand each country, how much they have under production, whether they're going to import food or export food, where they're going to get it, how we as a planet of humans can survive. Space is now such an integral part of that information that we can't go back. We must continue to go forward.
By the way, that takes me to, can I just jump in really quickly, David? Yeah, so that takes me to that Buckminster Fuller story where a young journalist is nervously asking the great gray eminence Buckminster Fuller in his 70s, interviewing him. And at the end of the interview, he says, Mr. Fuller, you have spent a career prophesizing about our destiny in space. Does it bother you that you've never been in space? And Fuller looked at him in amazement and said, my God, man, where do you think we are? Isn't that a great story?
Planet Earth is its spaceship, and it's a big one.
Yeah, and he was a big proponent of that.
Yeah, yes. Absolutely.
Yeah. So
Sorry, David. What were
no,
you
no,
gonna
not at
say?
all. Actually, I just wanted to ask Jim, because I'd never heard that before, that we're the first species that can anticipate or
Yeah.
recognize that we. I wonder, are we also the first species that could cause its own extinction?
Yes.
Is it? I mean,
Well, I'd have
is
to
that
think
true? Do you
about that.
think?
It's certainly true that we are a species that could cause our extinction. There's thoughts in that area. I mean, when you talk about nuclear war, we invented that and we were moving towards that. And we now know that releasing, a certain number of nuclear bombs would create an environment that we would not be able to survive, even though a significant number of people could have lived through nuclear wars. But it's the changing of our atmosphere that then prevents sunlight from getting down, and the radioactivity aspect of it that would then eventually kill our civilization. And so that's an existential threat. It's there. We've been able to move on and deal with it. There'll be others, and we must be able to overcome these things. And we have to do that as a world, as the human species on this planet. And we can do that. Okay, we just got to keep at it.
This is why I'm looking for. I find that the vibration between state changes and state changes. I think we have to work on both to keep up. It's part of the scaffolding that we're building. We need to be able to do the sort of deep work of a new vision of a social political in order to be able to survive the kinds of time that we're talking about.
Yeah, in fact, it's just in my scientific career, I have seen such enormous changes, such that we recognize there's other risks that were unknown, such as being hit by a very large asteroid.
Right.
And now, since we've become aware of where we are in space as Earth orbits the sun, we recognize we're not in a very good orbit. We're actually in a horrible orbit. There's at least 60,000 objects across our orbit that's going to hit us. It's not a matter of if, it's only a matter of when. And some of them are absolutely huge. I mean, the size we believe of the impact that created 80% of the extinction, and with the dinosaurs, dying off, is only about 6 kilometers. And there's some of these that cross our orbit that are 30 kilometers. That is an extinction event of everything on this planet. So we now know these things. And once again, it's not a matter of if, it's only a matter of when. Now we can, because we know about them, do something about them, develop capability and programs to do it. In fact, in November, we're launching a mission called DART that's going to hit an asteroid and move it. This will be the first time we've created a planetary defense mission. Fantastic. Okay. We've gone from, in my scientific career, total ignorance. It's like letting your 2-year-old child play in the busy street, not thinking you were going to get hit by a car. Well, you're wrong. The probability is there. You're going to have to face it. And then not only thinking that through, figuring out what's there, trying to find everything, and then begin the process of mitigating it. It's really phenomenal what we do. And we needed to do that. If we just turned inward, we would be surprised as the dinosaurs were.
Right, the dinosaurs didn't have a space program.
Let me share a couple of questions coming in. Yedil is asking, it says, for me, it is super important farm spaceship on the mega level. Is there any designing or blueprints for that? Farming spaceships.
Yeah, so we've started that process. And farming to me means growing food, right? And indeed, on space station, there's an area where we're growing food using what we call hydroponics. This is the ability to have plants suspended in water with the right nutrients. And it turns out it's one of the most fantastic places on space station. You know, everyone talks about the cupola. The cupola is that window that looks down that astronauts go to look at and recognize this is our Earth. They don't see the countries, the boundaries, the borders. It's Earth, and recognize how fragile it is, and really come back and feel as an Earthling how dedicated many of them become in terms of conservation and sustainability, in reuse, and getting very much involved in that. And that's called the overview effect. There's another overview effect, I think, going on. And it's when they go into the green room with all this vegetation and they smell it. You know, it's a different sense. It reminds them of home. And then they, you know, they're working to develop these in a way that have one green meal, you know, a week, you know, is what they would like to do, what they would prefer to do. That's probably one of the themes on going, you know, to Mars, and is how to develop that. So we'll have to have some sort of modules that will be very agriculture in nature, and they'll be wonderful, and they'll be maintained because all the astronauts will want to go in there and smell them and get that green overview.
Yes, great.
I have another question from Monica Lacey. It says, speaking of time, and you mentioned planets maybe having been inhabited, but that moment having passed, does NASA do any exploration of time alongside the space exploration? And then it says, and yes, I'm asking about time travel.
Okay. I didn't think of it that way, but no, you know, right now, time travel is still on the drawing boards with, you know, equations. Indeed, the concept of looking at planets and their geology, you know, one of the things that we're doing is coring rock right now. We've done our first core. You know, that core is about the size of a piece of chalk. And for those in our audience that are too young and never used a blackboard, I'll just say a large Crayola crayon, okay? And that's now in a tube, and we've got, you know, 40 tubes or more that, you know, our hope is to fill up, and then we're going to bring them back. Well, the rock record is that geological record of that planet. We know Mars was a blue planet. It lost an enormous amount of water, okay, over time. We don't know, we believe that climate changed rapidly, but we don't know how fast, you know, how fast is rapidly. Is it 10 million years or 100 million years, okay? And then when exactly? We think it was like maybe 3.6 billion years ago, just about the time the climate started to change on Mars, life started here on Earth. If that's the case, then maybe life also started on Mars and then struggled to survive and then died. So also in the rock record will be an understanding of whether there potentially was ancient life on Mars. For instance, here on Earth, there are over 5,000 minerals that we've identified, and 300 of them or more on that order can only be made with life, with dead life, okay? Forms part of that rock record. And so right now we know of about 280 or so minerals on Mars, and none of them are different than what we have found here on Earth, but the rock record that we bring back will greatly expand that number and maybe give us that first indication that indeed there was life on Mars early on.
Can I say something to Monica about time travel? So, you know, actually, in a way, we do have a time machine, you know, in orbit. It's called the Hubble Space Telescope. And that and other telescopes are able, but especially the Hubble, to look deep into space-time. And for example, multiple images from Hubble look at some of the earliest galaxies discernible. with our current technologies. And you can see the evolution of galactic forms in some Hubble images. But apart from that, so that's looking deep into time in such a way that it's producing empirical evidence of how we came to be in our contemporary Milky Way and what the morphologies are of other galaxies and how they might form. And you know, I mean, there's an image that I was thinking about recently where there's one spiral galaxy suspended in front of another, such that it was silhouetted such that the lit part, we're used to looking at the lit part of the galaxy, but we don't know how much unlit area there is extending out from that galaxy, not starry stuff, but other material, gas and dust. But this was suspended in front of a larger galaxy such that you could see all of this dark material extending out on all sides of that galaxy. So that's looking into the past and looking at the evolution of galaxies and the design of galaxies. But also Hubble, for example, when Hubble looked at various nebulae, the Carina Nebula, for example, it produced images of stars forming in multiple phases of forming. Protoplanetary disks, a frisbee-shaped disk of gas and dust where you don't see a star yet. You might see a kind of a coal at the center. It looks like something glowing at the center. It's the star beginning to form. So that's time travel right there, because it's not our system. We're not going back into our system. We can do that with core samples, as Jim was saying, but it is looking at the evolution of planetary systems. So we're definitely, unfortunately, we don't have the ability to go forward in time apart from at 1 Earth day per day. We're all moving forward in time.
And of course, a lot of that field that you're talking about is called cosmology.
Yeah.
And, we have many astronomers that really tease that out, letting us know, well, the age of the universe is 13.6 billion years. And the sun actually, is what we would call a second generation suns. Other suns have come and gone, exploded, created material for which our sun is now created from. And in that also comes the planets that start around us. That knowledge was not well known, and it's really looking out in other systems that help us put that picture together.
By the way, one thing I would say about Clubhouse is that the people who join later might not know that the way to ask a question from Clubhouse would be to text it rather than.
No, actually, yeah. Thank you for saying that. But I do have a number of questions from Clubhouse.
Very good. I'm going
to get to some of them right now.
I can't see those. I'm just seeing the ones in Zoom.
Yeah. No, I have some. This is from Goli Imami. Oh, wait. The question just didn't. There it is. I heard Jim talked about sustaining human species for millions of years through space architecting. What are his thoughts on human species evolution and how this species would change or potentially evolve into multiple species if we manage to survive? Is he or NASA thinking, dreaming about that?
All right.
Great question.
Okay. So I know through talking with biological friends of ours and that are in these fields of evolution that, we as humans are continuing to evolve. Evolution comes about based on stresses and strains, and then the ability to accommodate the change in our environment. Over time, we may be able to mitigate some of these huge changes in our environment that we are destined to have. And therefore, there may be some different aspects of evolution, but we will evolve also mentally in our abilities, the capability to learn. We're also moving into an environment for which we understand much more about DNA and RNA and the genetic codes and how to repair them. So, Michael, one of your earlier thoughts on going into space and having cosmic rays what they do is they will destroy strands of parts of DNA that then actually, through certain technologies, can be repaired. And in fact, we're finding out there are some genes people have that go to that process and do some of those things on their own. And so there's a proclivity that occurs on certain things that our body does naturally because it's evolved that way. So evolution is one of the hallmarks of life. What NASA has decided is that our working definition of life is that it has three attributes: metabolizes, reproduces, and evolves. And if we can find something out in the solar system that does that, doesn't have to be, carbon-based like we are, we're going to call it life. And so evolution is going to continue. It's one of those fundamental things. What it will be in the future, I have no idea.
All right, I have another question that is very specific, but does resonate with this
All
one.
right.
Dorian Rednaxala. Between Dragonfly and the Clipper, which will more likely change the way we think about the moons of Jupiter and potentially life?
Both.
Wait, is Dragonfly the European mission?
No, Dragonfly, JUICE is the European mission, but
right.
Dragonfly is going to Titan.
Ah.
Okay, so what I really like about Titan is that if there's any place in the solar system where there might be life not like us, it's on Titan. And the reason why is it has liquid on the surface, and that liquid is not water, okay? It's methane and ethane. And so as I go back to the definition of life, metabolism requires a liquid with food that then is used as a solvent, and then the liquid eliminates the waste and you take the energy. And so a liquid is a key element of the metabolism process. For us, that's water. And so when we started the process of looking for life in the solar system, we can't find cell division and we can't find evolution, but we can follow the water. Let's look for places where there are signs that water existed, and therefore that's a potential place where life might have been. And those indications on Mars are all over the planet. From the minerals that it's formed to the telltale signs of the ancient shoreline on the planet, etc. But on Titan, the liquid is methane and ethane. And so if there's life there, it's using a different solvent. And indeed, that's really tremendously exciting. So it helps us in two ways.
And in fact, the rocks on Titan are frozen water.
Yeah, many of them on the surface are. Yeah, that's right.
A lot on the surface.
Well, here's an interesting one from Joshua Fisher. How much do looks play into design for spacecraft and stations and the like? Like the way they look in terms of,
aesthetics.
Obviously something's appearance in terms of design
Can I take a stab?
Sure.
Let me take a stab at that. All right, so for those on Clubhouse, I'm holding up a design of a wheel-shaped space station from 1929, produced by a very elegant wheel-shaped space station where at the center there's zero gravity and at the rim there would be artificial gravity because it would be spinning. And there's a very nice curving corridor between the center and the outer part. Now, this is a very elegant piece of design and architecture from 1929 by Hermann Potočnik Nordung, who was a Slovenian Austrian Habsburg citizen. He was a citizen of the Austro-Hungarian Empire. People don't think about that empire anymore. He was Slovene ethnically, and he published one book which was called The Problems of Spaceflight, and he had this beautiful design. Werner von Braun borrowed this beautiful design for his depictions of what a space station should look like in the 50s, which Walt Disney, he collaborated with Walt Disney, and we had wheel-shaped space stations in the 50s. Arthur Clarke and Stanley Kubrick then borrowed Werner. By the way, Werner von Braun did not credit Hermann Potočnik-Nordung. It helps to be a citizen. Well, von Braun was then a citizen of the United States, but he was a German. But it helps to be a citizen of a country that still exists. The Habsburg Empire vanished. In any case, the beautiful wheel-shaped space station in 2001: A Space Odyssey came from Hermann Potočnik-Nordung's design. As for design, aesthetics of design playing a role, certainly if you ask Elon Musk, they do, because he wants his starship to look more like a Buck Rogers spaceship. Science fiction has influenced design in his universe. I don't know, Jim, you would be the guy
I would
to
say
talk
for
about.
NASA's approach is utility first, aesthetics later.
Aesthetics maybe never.
Well, if you can do it and it looks nice and it doesn't cost more, we'll have it.
Actually, this
although a 2-camera shot on a parachute could be really, really great.
Yeah, actually, you're so right. I mean, when you consider how many cameras were documenting the descent of this last rover and how incredibly aesthetically compelling the whole descent was, it's not correct to say aesthetics never. Aesthetics are there. It's just that, when it comes to the actual design of the spacecraft, it has to be utilitarian.
All right. Okay. So thank you very much. I appreciate that because, indeed, I had to find the money for all those cameras. But I will mention one thing. One of the things that I really wanted was audio, and there's, so the scientific for Mars, any of the Mars, anything going down to the ground, we ought to have audio on it. And I had a heck of a time convincing anyone to spend any money on audio because it sounded so frivolous until the idea came along. Well, as the rover moves, you're going to hear the creaking and the cracking. You're going to hear, what may be parts wearing out before they wear out.
You have a utilitarian reason.
Then it was gold. And so now we have two audio systems on Perseverance.
By the way, I was privileged to be at JPL when Cassini arrived. Earlier, I mentioned being there a few months before it arrived, but I was also there when it arrived. And I got snuck into the first meeting of scientists, with the chief scientist of the mission. And then I got kicked out when he realized there was a journalist there. But I was in there long enough for him to play, I forget his name now, chief scientist of Cassini at that time. But Cassini had a dust detector.
Yeah.
And Cassini flew through the ring plane on arrival.
Yes.
And so they converted that data into sound.
Yes.
And what you heard was, chunk, 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 chunk. And then suddenly there was this crescendo of sound as Cassini passed through all the dust of the plane of the ring, and then it descended to zero again. Yeah. And, it was kind of scary in the sense that you knew that Cassini was, flying through a zone that had enough in it that it could make that sound. But it's an example of sound in space, even if it wasn't literally.
So this heard. Indeed was one of the reasons why when JPL proposed, how are we going to end the mission? We were all concerned about Cassini hitting Enceladus and Titan in particular, because its orbit goes out 20 Saturn radii, which is where Titan is. And so if it runs out of fuel, it's uncontrollable. We can't do anything. It then becomes something that can impact these other worlds. So the discussion then clearly centered around, we ought to probably ditch it in Saturn. And now you have the difficulty of you have the ring plane in the way. And so JPL did a fabulous job constructing a series of maneuvers that got real close to the outer ring, did a gravity assist at Titan and jumped inside the ring, okay? Knowing, or taking the chance that, that might end the mission because we don't know the amount of ring material that's falling onto the planet. We know it must be falling on the planet, but we don't know how much it's falling onto the planet. And so the rings are literally wasting away. And so is the spacecraft going to survive? So I'm the one that signed off on that maneuver, that indeed we were going to end up jumping inside the rings, and then after a certain number of orbits, finally do a plunge. But it was a gutsy maneuver, and man, we learned so much by doing that. It's another one of those things that we have so many talented people being very creative and talking about how to get the most out of our missions, that we now know the rings, literally, which are icy material, are heated by the reflected light from the planet, and there's literally ring rain coming down from the rings down on the planet, and then we can taste that, as we fly through it. We took a variety of measurements, and really, it was really phenomenal. And we got the gravity of the planet too, meaning we then could tease out what the structure of the interior looks like, and it's very different than what we thought. It has a nebulous core, where we expected the core to be a very important demarcation. It's not at all.
When you say demarcation, a rocky body in the center, but it's not like that.
No, it's not like that.
Is it liquid metallic hydrogen? Does it turn into a kind of a liquid? Well,
so what I mean by demarcation is at crushing depths,
yes,
you have transitions where higher mass material will flow to the interior, and then you get to the point where you run out of some of that mass, and then you see a rapid transition to a lighter mass. That's what makes our core, mantle, and crust so distinctive on Earth. And the core, indeed, has Saturn has a lot of hydrogen and helium, and so there is metallic hydrogen, and it's very nebulous. There's no one of these really nice drop-offs as we expected.
I think I heard you say recently, and I hope I didn't misunderstand this, that inside of Europa, deep, its core is something like Io.
Yeah, of course.
Did I understand that correctly?
Yeah, you did.
So there's an Io inside of.
Yeah, there could be volcanism. There could be subsurface volcanic activity in the seabed of Europa producing energy.
Has to be. Has to be. That's what's keeping the ocean there liquid.
Well, there's also the flexing of the crust, right? Isn't there friction generated heat?
Yes. Yeah. So because Europa is an elliptical orbit, when it's at perigeo, which means close to Jupiter, Jupiter's squeezing on it. And then as it moves to the other side, a day and a half or so later, and it's at apogeo, which means it's further away from Jupiter, the squeeze isn't so much. And so it relaxes it a little bit. And so if you just took it out and looked at it, it's flexing like this every orbit, which means the surface moves up and down 30 meters. Okay, that's the height of a 9-story building. It's taller than NASA headquarters.
Yeah, and then
the
also
ocean is water because there's volcanoes deep under it.
That and you have to dissipate that heat somehow, and it then melts the ice and keeps the water liquid.
But another important thing to say here is that we believe there's a strong body of evidence that life originated on Earth at subsurface volcanic cracks at a time when the surface of the planet was being bombarded by heavy, incoming asteroids, as we discussed, and so life may have started down there, and so it's quite possible that in Europa, that's one reason why Europa is so endlessly fascinating.
Correct.
There's life on Europa.
So I think so.
So also in our lifetime, I'm looking at the three of us. In our lifetime, we discovered here on Earth hydrothermal vents.
Right.
1977 was the first hydrothermal vent deep in an ocean. And now we've been to about 300 of them. And every one of them, you know, they have different temperatures. They have different, you know, some are acidic, some are alkaline, you know, huge range in pH. But each and every one of them we visited are teeming with life.
Teeming, swarming, yes.
Yeah, it didn't require any sunlight.
Right.
So
Right.
conceptually, you know, knowing that the ocean floor of Europa must be, much like Io, being turned inside out, also dissipating the pull and tugs from Jupiter, we would expect hydrothermal vents. And in fact, we can see, and even in the icy crust, some indications where hot waters has come up. So, and maybe even trapped, water gets trapped in between some of the upper ice layers. So Europa is going to be pretty fantastic. And we have an ice penetrating radar to really give us a great view of what that cross section looks like. And where it's thin, where it's thick, and perhaps really get us an idea how these cracks open and close.
I've always loved Michael's images of well, of all of them, of our solar system and beyond, but the images of Europa and Io have just taken my breath away. I mean, I often say that that's Europa, the surface of it, is the largest drawing in our solar system.
It's like a Rorschach.
Yeah, it's a drawing. It's being made by all the gravitational push and pulling that you're describing, but I think it helps when we think of that. And that, I think we're going to take one last question I'm going to share, and
Can I just say very briefly, when David says Michael's pictures of Europa, it's those are assembled using raw data from interplanetary missions. So what I do is I assemble them and I produce large format photographic prints of landscape.
Right.
Yeah, Michael wasn't out there with a tripod.
No.
Sorry.
I wish I could go, but you know, I would die of radiation in about 30 seconds anyway. So.
Or less.
Yeah.
No, but speaking of both of these things, I think this is a very hopeful and interesting question. It's from Rose L in Clubhouse.
Yep.
Well, it starts saying NASA aesthetic is arguably its own thing, which I like. And it says, I have a question re art in space and architecting artistic missions in space. It would be amazing if NASA could bring back the NASA art program. Could we have an artist in space thanks to NASA to help inspire the public?
Okay, I mean, I like that idea. NASA actually has been talking about crew composition in station, and the concept.
I volunteer.
Okay, all right.
But I think Tom Cruise will get there before me, unfortunately. No.
Yeah.
Sorry, Jim. Go ahead.
Well, I was just saying, it's a great idea. Yeah, it's a great idea. I do like that. If I have any influence in that, which I don't, but if I ever did.
Oh, come on, you're chief scientist. You know, if you don't have influence, who does?
I don't pick the astronauts. I don't pick the astronauts.
Yeah.
You know, the astronauts are selected in a very closed, methodical manner. You know, where you know these people that they pick, type A personalities, have depth, are energetic, can lead a team, but then be a follower. You know, some of their best traits are all interpersonal relationships, so that they can work together. And so whatever that mixture is that they look for when they pick astronauts, I have no influence over.
But you know, Elon Musk, I think they're already planning privately staffed missions with Elon Musk's what is it, the crew capsule, what's it called, Dragon capsule, and I believe that there will be artists eventually going into space in that way, for sure.
Yeah,
and there is talk of filmmaking, big budget Hollywood to consider that art, which sometimes it is, sometimes it isn't.
Well, I'd be really remiss if I didn't point out two astronauts that are well-known artists. One is Alan Bean, and the other is Nicole Stott. Now, Alan unfortunately has passed away, but Nicole is really wonderful. I mean, she has all sorts of wonderful ideas that she expresses in art. So if you ever follow her, she's actually on Clubhouse. If you ever follow her, you're in for a treat. Really a tremendously wonderful person and a fabulous astronaut.
One more footnote to that question, if we have a minute. Do we have a minute,
Yeah,
David?
of course.
Okay, so who asked that question? What is the name of the person?
Rose
L.
Yeah, so Rose L. I have the honor of working currently on a project with a group of people internationally called Sanctuary. And we are working with NASA to land a time capsule on the surface of the moon containing 24 synthetic sapphire disks, each of which will have not digital information, but analog micropixels etched into each of them. Sapphire being the third hardest material that we have. It's designed to last for millions of years. And it's an art science project in the sense that its cargo is a curated set of the best examples of human genius for 4,000, 5,000 years, curated by various people who have specializations in various fields. So this is an art project. It's not literally by somebody, no one of us is going to space, but it will be on the surface of the moon via the good offices of NASA, which is landing a series of robotic missions on the moon prior to landing human beings back on the moon at the end of this decade. So that's an art project in space for sure.
I just wanted to say, I'm gonna, it's embarrassing because I cannot remember the names, and I'm sure you both would know. But I was recently listening to a podcast called Anthropocene Reviewed, and it was going through in detail a space mission, and I believe it was Russian. I believe it was early on. And one of the key points of it, and I'm sorry, I can't remember the name of the cosmonaut or any of those details, but one of the key points of it was after a number of very life-threatening circumstances. I mean, like barely being able to get back in through the chamber and like really scary stuff. The cosmonaut took out paper and markers and made a drawing. And partially the description was to calm himself down because he had almost just died. But it was also this, elemental drawing of the sunrise, the Earth sunrise, right? The sun coming up behind the Earth that he was able to see. And I think it's John Green who does the Anthropocene Reviewed, just really made this astounding point about that moment in that person's life and in the life of humanity, where making a drawing was the appropriate response to this existential threat.
So that was Alexei, that was Alexei Leonov, who was the first man to walk in space. And what happened was, his spacesuit, inflated. They didn't take into account the fact that the spacesuit really, it's like a balloon. It expands. He got out, but the spacesuit was was quite large, Michelin man large, and he had to fight like hell to get back inside. And of course, that was a life-threatening situation. I believe he had to vent air and risk the bends to get in. And then when he got in, I didn't know that story about him drawing, but Alexei Leonov ended up being one of those artist astronauts, or cosmonaut artists, I should say.
Mm-hmm.
Yes, and he did a lot of paintings later, so I guess that might have his career as an artist might have started right there.
Amazing. Well, I think we should wrap it up. I just want to share one last thought that came to my mind, linking a few of these things, which is when Jim, when you were talking about getting sound, like working to get the sound, and you had an instinct that you really wanted sound, and of course then you found the utilitarian justification for it. Right? These are big budgets, but I'm fascinated by the fact that you also just knew we need sound, and that and this goes back to the question of art in space, etc. I feel like there's something about sensory perception, meaning you're adding another layer, another dimension. Maybe we need olfactory as well. You know, we know there's a lot going on there. And also about gravity, like if we think of our senses, and you think of our friend Chris Rose is always talking about our sense of balance, like balance as a sense. You know, you have a sense of balance. Without it, you're pretty, you know, lost. And the last couple of exchanges made me think about the imagination as a sense. Meaning everything that we're talking about is really only possible because of our capacity to imagine.
That's where it starts. That's the first. Yep.
And by the way, that takes me back to the great Konstantin Tsiolkovsky, who came out with this incredible pronouncement at the turn of the 20th century. Earth is the cradle of the mind, but humanity cannot remain in its cradle forever. Now, this has been translated differently. And my mom happens to be a translator of Russian, and I ran it by her in its original Russian. She translated Sergei Khrushchev's memoir. She's very good. I'm going to Vermont this weekend for her 89th birthday.
Oh, wonderful.
And
congratulations.
Thank you. And anyway, because it has been translated, Earth is the cradle of humanity, but humanity cannot remain in its cradle forever. But the word was mind. Earth is the cradle of the mind, but humanity can't remain in its cradle forever. So what does that say? It's about imagination, you know.
Yeah.
And it's not necessarily, it's about our minds leaving the cradle as well.
Mm-hmm. That's a really nice point. I like that.
Well, listen, I want to thank both of you. This has just been extraordinary. It really, for me, it is a dream, you know, as I said in the beginning about light. And I always think it's fascinating that a physicist and a photographer both consider light to be, the basic stuff of their work.
Sure.
And here we are. And I've said for years, if we really want to get after the hard challenges, we have to bring together as broad a spectrum of ways of knowing as possible to ask the shared questions. And this is exactly what we're doing. So thank you both so much for this.
Thank you both. It was really a lot of fun and a delight for me.
Well, it was me too, delight. Michael and I have had a long-term friendship, love to talk about these things in many different ways. The exchange of views has just been wonderful. And I'm so delighted, David, you had an opportunity to draw that out of us tonight.
Absolute pleasure. And I'm sure we're going to find more ways of playing together.
All right,
let's do that.
All right. Well, thank you, everybody, for coming. And
yes.
We'll see you again real soon.
Yeah.
Thanks
to
so
everybody.
much. Take care.
All right. Take care, folks.